So, last time we are talking about heat conduction, and I have shown you how to derive the governing energy balance equation in Cartesian coordinate system, starting with the Fourier's law and an energy balance statement. And if you remember, the equation that I wrote, which can be represented or was represented in terms of this parameter, okay, in which k deliberately I have assumed to be constant, and I have also said, if you remember, that rho and Cp are also constants. So, this was basically, or this is basically the governing energy balance equation or governing heat conduction equation in Cartesian coordinate system. And as far as the derivation of this was concerned, I had written some statements and I talked about linearization, but you must remember that the statement in word is equal to, for example, I would say rate of, I am not writing it, so it is output. So, I say rate of output is equal to input plus generation. So, this is the basics of the balance, energy balance, and this statement is basically valid when you have a steady state operation. That means, the rate at which heat is output from the volume element is equal to rate at which heat is input and rate at which heat is being generated within the control volume. But changes to an unsteady state, then this particular statement unsteady state, then this particular statement will get reduced to, I will say that it is input plus output, input plus generation minus output, and because it is unsteady, the temperature is either going to go down or going to go up depending on the imbalance between input and output plus generation. So, we can say that this is equal to accumulation. So, this is the net rate of heat accumulation. So, that becomes the statement based on which this was derived. I did not show deliberately, have shown you the details of this statement as well as step by step derivation, assuming that you have already been exposed to the derivation much earlier in your undergraduate classes. So, when input plus generation is greater than output, then the accumulation becomes a positive term. So, the temperature increases as a function of time. This term accumulation is the partial derivative with respect to time. So, the time will increase as a function of temperature. On the other hand, if the output from the control volume is greater than input plus generation, in that case what happens is we have a net decrease in temperature. That means, the temperature is going down as a function of time. Now, this was the equation in our XYZ coordinate system or the Cartesian coordinate system, and if I have to write the equation in the r theta z coordinate system, then this, because these statements are going to be useful in expressions. So, that is why I want to write these equations for you, but they are available in textbooks and you can note them down. So, the unsteady state remains the same, and we have here, if I expand this term, then this becomes for a constant k. So, I take the k out of the bracket, and this is the z directional derivative plus this is the r directional derivative and this is the theta. This is the r, okay, and this is. So, this the bracket is closed here, and I would just, because there is an overlapping here, so I would write to close the bracket. And then of course, we have the net rate of heat generation term, which is the volumetric rate of heat generation in cylindrical polar coordinate. Little bit complex features have come because of the geometry involved, and the same equation, if it is written in terms of r theta and phi, in that case this expression will look something like, again k is taken to be constant, and this is I will write 1 by r square, this is the radial direction term Now, instead of here it was r, and if you put, actually the beauty of this is if you put r is equal to 1 here, okay, and interpret that the radial coordinate is your y direction and the theta coordinate is your x direction, then this equation can be visualized as the same as the Cartesian coordinate equation. Okay. So, this is the radial direction term, then we have the theta direction term, and here we have r sin theta and sin theta, and then we have here r square sin square theta. I hope I have written the correct thing, and this is we have this square theta over this square double partial with respect. So, these are basically the three equations. You can verify them. Maybe I have made a little bit of mistake here and there, but I think that these are the correct statements, whatever I could recall, and these are the three corresponding expressions of energy conservation for a conduction problem in three different coordinate system. Now, let this be the starting point of today's discussion, and let us now proceed with our proceed further in the course and see that how can you simplify. We will, because two-dimensional and unsteady one-dimensional equations we will not be able to solve here analytically. Of course, one-day unsteady state solution in Cartesian coordinate I will show you later on, maybe tomorrow. But in general, we will, for today's lecture, we will consider basically steady state phenomena and one-dimensional heat conduction, maybe in Cartesian coordinate, maybe in cylindrical coordinate, or maybe in spherical coordinate system. So, let us look at the simplification of the Cartesian coordinate system problem. So, we go back to the left side of the board and say we have x, y and z. Okay. So, Cartesian coordinate simplification. And this the simplifications, as I said. So, number one I am going to apply, I am writing in brief, steady state, this holds good. All the problems that I am going to discuss and we are going to solve in tutorials are going to be with constant thermophysical property, constant thermophysical property. That means the density. We may solve one or two problems with variable thermal conductivity or temperature dependent thermal conductivity, but that will be taken up when we solve the tutorial problems. We will do also today basically 1D, okay, and number 4, the simplification that we will apply is no heat source. If you do this, in that case what happens that this equation, okay, the unsteady term will vanish because it is a steady state problem, because it is a one-dimensional problem. So, therefore, only one derivative will remain. If I say that as far as the drawing here that I have the geometry is like this. So, the derivative along x stays, y and z which are perpendicular to the board, the derivative vanishes because it is a 1D problem, and therefore, the equation and this term is also going to be equal to 0 because I am considering a scenario where there is no heat source. So, therefore, the governing equation will look like this is the equation. And then as I have indicated and you all know, look at the derivative immediately, you can say, sir, I did two boundary conditions. So, if this is x is equal to 0 and this is x is equal to L, and then we can solve this equation. So, x is equal to 0, t is equal to suppose t naught, x is equal to L, t is equal to t sub L, and then we can integrate it twice with the two boundary conditions. We can say that this equation will look like the temperature between x is equal to 0 and x is equal to L will vary as A plus Bt in a linear fashion. in which A and B are the two constants of integration which is to be determined. And because applying the boundary conditions, because this is a straight line, so therefore, this essentially tells us that the solution, if I say that T0 is greater than TL, okay, in that case, and this axis represents temperature, then the temperature variation will look something like this. And if you take the gradient of this, what that gradient means? This becomes differential T with respect to x, and if you multiply it with the constant thermal conductivity, it becomes the flux, and because it is a straight line, so that means the flux at this point, the flux at this point, the flux at this point, all are going to be equal. So that means whatever is energy which is going into the system is exactly what is going out of the system itself, and this is happening here because the area perpendicular to the board is identical. These are infinite areas, as I have said, because the only dimension across which is meaningful. You must understand that when I say that if you have a derivative something like this, and I say the z direction is infinite, so therefore, what happens is, from a dimensional reasoning you can say that there is going to be no temperature gradient along the z direction if the span of that direction is very, very large. So, the finite direction is only in the x direction, and therefore, the flux at any point is equal to constant. In a one-dimensional context, flux and the rate of heat flow are going to be all identical, okay? Because there is parts say there is no area here, area is undefined parameter. We normally take that area 1 into 1, okay? Along the y span it is 1, along the z span it is 1. So, that represents the area. So, Q multiplied by 1 into 1 represents the rate of heat flow. What? Similarly, Q multiplied by the area, and the area at this particular phase at x is equal to 0, and area at this particular phase, they are both identical. So, therefore, we can say that the heat flux is same, and as well as the net rate of heat flow is also same at any point between the bounds x is equal to 0 and x is equal to L. Now, if we have say two different materials here, or let us first introduce the term. Now, in this particular context, when we write Fourier's law, if you remember, so we write k minus k, and this basically we can say whatever I have just now said, that if we multiply it by q into a, then this becomes our net rate of transport. So, capital Q, we should always know that this is what? Small q, which essentially represents the flux, which is watt per meter square, okay? And that gives us minus k A dx. This essentially tells us that the flow basically happens like minus dt, and then we have dx over k into A. Now, if you remember, if you look at this equation, or we can write it like also what flows is heat, okay? The driving force is the temperature differential, and if you apply it to the electrical circuitry, and you see that there is one-to-one correspondence between Ohm's law and Fourier's law, where it says there in the context of Ohm's law we are finding that it is potential difference. The current is flowing because of the potential difference, and the proportionality constant is the electrical resistance, and in that case what we get here is nothing but the thermal resistance. Okay? So, this term let me correct it, yes, on the denominator represents essentially the thermal resistance of the system. So, that is what, if you have delta x, if this is delta x, in this context, because there is no area, so take the delta x divided by k, and then you get what is known as the thermal resistance of this particular one-dimensional block. Now, the thermal, as you can see here, that we have temperature here. So, therefore, if you see that R thermal, I would note now, let us say R thermal is equal to dimensionally delta x over K A, and that we have, if you now substitute the unit of delta x meter, K is in watt per meter Kelvin and A is in area, then you can say that it comes out to be in the unit of Kelvin per watt. On the other hand, if you can express the thermal resistance per unit area also, in that case what you are going to get? You are going to get, if you use the basis instead of K, Q, you apply that the definition of Q to deduce the thermal resistance. In that case, it is Kelvin meter square by watt or Kelvin meter square per watt. So, in 2 units you can encounter depending on how you have defined your thermal resistances. Kelvin per watt will come out when you have defined it with like this, but the area has come into the picture. On the other hand, if you define thermal conductivity, I think defining it with respect to the net rate of heat flow rather than flux is more important for us, because conceptually it is the heat which is flowing and not the flux. Okay, but in the one dimensional context they mean one and the same thing. So, therefore, these are the 2 possible units in which we can express our thermal conductivity. Most of the problems or most of the time we will consider this particular expression, and based on this we will derive that what is the applicable thermal resistances in the system. We will find out that what is the thermal resistance in other coordinate system also. Now, if we look at the application of this concept is very straightforward and is beneficial. Suppose we have now, I say that 2 different materials, okay? One is A, another is B. These are composite materials. And I say that this is delta x1 and this is delta x2. The span, still a one dimensional problem. It is only along x, y and z are infinite. And this has a thermal conductivity of Ka and this has a thermal conductivity of Kb. If this temperature is T0 and if this temperature is TL and T0 is greater than TL, so we can say that the temperature will look something like this. It is a one dimensional problem. One aspect we understand here that the slope on the interface on left hand side is exactly equal to the slope on the outside, and slope is a measure of heat flux. So, we say that at the interface there is a continuity of heat flux. Whatever is the flux or total energy in this particular case, which are synonymous, leaving A, it is exactly the same thing which is entering B. So, the continuity of heat flux is to be maintained at the interface, and in this particular case we can say that, look, we can say Q is equal to T0 minus TL, okay, and then we can say that what is the thermal conduct? We can say that this is R thermal A plus R thermal B, the total resistance, because they are operating in series. Just like an electrical resistance, we will add up the resistance and we will get the net rate of. So, if these temperatures, which are boundary temperatures, which will always be given to us, thermal conductivity will also be given to us. Okay. Similarly, the span of or the domain length will also be given to us. So, therefore, the thermal resistances can be calculated very easily, and therefore, we can find out that what is the net heat flux or the net rate of energy that is taking place. Change this problem to an equivalent scenario. So, this is now, I would say, draw a partition line here, the same problem, but I say that, look, the interface now, when you join 2 materials, the materials joining, these are composite materials, the joining may not be perfect. Okay? So, there may be an interfacial resistance between the 2 material itself. I have exaggerated it, but this could be just couple of microns or maybe in some cases few nanometers. Okay? For example, you can imagine that when you line a refractory vessel, okay, the outer thing is the steel shell, but then you put the refractory on the steel shell, there is a certain interface between the steel shell as well as the refractory. So, there is no perfect contact between them. So, there is always inhomogeneities at the contact. So, the contacts also have because it can have impurities, it can have air entrapped. So, therefore, we will discuss this interfacial contact resistance between the two surfaces when we will talk about the applications towards the end of our lectures on heat conduction subject. But for the time being, this is the case when there is a perfect contact between A and B. On the other hand, this is a scenario on which we have imperfect contact and there is some kind of a resistance at the interface. So, now what happens? You have and then we have goes down, interface drops and then again it goes down. So, that is the kind of a temperature drop that really takes place in this particular case. Now, even if you have this kind of a drop, so this interface is, because there is a drop in temperature, so therefore, we assume that there is going to be a finite resistance. So, this we call as an R thermal interface. Now, so therefore, in this particular case also, T0 and TL, okay, the continuity heat flux will be maintained, whatever energy is leaving, entering the interface is exactly the same amount of thermal energy which is entering the B part. So, this is our A and this is our B, this is our delta x1 and this is delta x2, and then we have a finite contact thermal resistance and therefore, I can add this is operating in series. We must understand that while thermal conduct resistance of A is known in terms of its thermal conductivity and the span length, our thermal interface is not known because it does not have a dimension. So, the thermal contact resistances are basically to be determined, okay, and this often happens to be experimentally determined parameters, that if you join a refractory with another refractory, you join steel with polymer, what kind of a contact resistances develop between the two surfaces, and this parameter therefore have to be supplied to you. This is one additional unknown on top of these governing equations. Okay? The temperature can be calculated, heat flux can be there, calculated given the boundary. If you have the governing equation given to us with the right number of boundary conditions, introduction of a thermal contact resistance brings in one more uncertainty. So, we become one equation and two unknown. So, therefore, I will demand that the thermal contact resistance have to be determined and given to us. So, most of the time, okay, and these contact resistances are very important in metallurgical problems. For example, if you remember, if you know that when molten metal flows through a ladle shroud from a ladle into a tundish, so it's a refractory vessel and molten steel flows, so there is a still refractory contact. Similarly, if you go to refractory lining of the vessel, there is a steel shell refractory contact. So, melt refractory contacts, refractory steel contacts, these are very common in metallurgical engineering literature. Even in continuous casting, for example, the first problem that I have discussed about the film flow and momentum balance in one dimension, you remember that I had a moving strand and I have a stationary mold, and between the two, very small place, maybe less than a millimeter, which is occupied by the downflowing film of mold powders. Okay? So, that basically is like a resistance between the two surfaces. So, the mold, it is not air filled space between the two surfaces, that is strand surface as well as the stationary mold one, but the space is filled, and there is now you have a powder mold contact and you have on this side powder strand contact. So, and this contact characteristics of this contacts are different. So, you may have a different contact thermal resistance on the left hand side of the domain and something else on the right hand side of the domain. So, we will discuss this and I will show you that how interfacial thermal conductivity can be determined by conducting trials. Okay? But this necessitates determination of both flux and temperature field, and then we should be able to find out and evaluate that what is this contact thermal resistance, which will be discussed towards the later part of the course. Okay? So, therefore, we can say that if you know the contact thermal resistances of A, the contact resistance plus the thermal resistance of B, in that case we should be able to find out the heat flux also in this particular case, or the net rate of heat flow which takes place here. Now, let us go into, so I hope that the one dimensional equation I have not shown, I have written you the, given you the final solution, the linear profile, and you should be able to now find out. For example, I want to discuss one more thing, that suppose if I say that, because it is an important point for you to remember, if I say still the same problem, one dimensional heat conduction, but with a constant heat source. So, therefore, I will write that equation as and what is this? This 5 essentially represents the volumetric rate of heat generation. Watt per 5 watt per meter cube is a constant rate of heat generation at every point in the one dimensional domain. So, now we do not have A and B, we have only one material, suppose. Of course, now the solution, same boundary condition applies, T is equal to 0 and this is TL, and now in this particular case, and T0 as I have indicated is greater than TL, and interestingly, if you look at this equation is absolutely identical to a fully developed flow equation with constant pressure gradient. Flow through a cylindrical pipe, and imagine that you had only one second order turn, that is along the radial coordinate, and we have the pressure gradient term which is the constant, because fully developed flow, if you remember, is characterized by a constant pressure gradient. So, this equation is analogous to the fully developed flow equation that we have derived for flow through a pipe, where the flow is taking place because of an imposed constant pressure gradient. So, therefore, if I say that if you solve this equation, no more you are going to get a straight line, you are going to get a quadratic equation. Okay? And if I say that both the surfaces are maintained at same temperature, this is also T0, this is also T0, and in that case what we are going to see? We are going to see a regular parabolic graph between the two, where the two extremities. Otherwise, it is going to get something like this sort of a scenario, where of course, we can if it is a cylindrical domain, in that case we can say that at the center line the line is going to be vanished, but in this particular case of course that condition does not apply. But if this, as I said, if you remember the symmetry conditions which I have also discussed, if the temperature on both sides are identical and then we have the line of symmetry here. So, this part is exact replica of this part. In that case, what we are going to see? We are going to see a regular parabola where the slope of the line will vanish, the condition of symmetry will apply, dt dx is going to be equal to 0 in this particular case. So, therefore, once we solve this equation with unequal or equal boundary conditions, nonetheless, we will never get a straight line, but we will get a quadratic velocity profile, and that can be a very regular parabola, just like the pipe flow problem, provided we have the same temperature. Because remember that when you have flow between a parallel plate, if both the plates, if I say, are maintained, we have a boundary condition which is no slip boundary conditions which are applied. So, boundary conditions on the two surfaces are identical. Between the flat plate, flow is taking place because of the pressure gradient, same as in cylindrical coordinate or the cylindrical pipe. So, there we have seen that the flow profile becomes a regular parabola. So, in this particular case also, if these temperatures are identical, so this problem becomes exactly, I would say, in Cartesian coordinate system, then the equation, this is absolutely identical to flow between two parallel plates, which is driven by a pressure gradient. Exactly the same equation will apply, and then you will see that this T will be replaced by the velocity, okay, which is the streamwise velocity reaction. X will be replaced by the y direction, but the distance of separation between the plates, and this will be the constant pressure gradient. So, it is the one and the same phenomena itself. So, the moment, however, we replace this constant term with a temperature dependent term, then the equation of course becomes a little bit tricky to solve. Okay? So, then the equation becomes a nonlinear equation, because this, if I treat that this is actually a source term which is a function of temperature. So, therefore, this source term is not known explicitly, and hence I have to really do an iterative solution procedure in order to find out that what is the solution of this subject to the boundary conditions which I have considered in the problem. Let us now go to the cylindrical coordinate system and discuss a little bit. So, in the cylindrical coordinate, if we apply the same simplification philosophy and we say that it is an unsteady, it is a steady state problem. So, this term is going to vanish, and I have an option to retain one of the derivatives only, because I will be solving again or demonstrating again on the board with one dimensional scenario. Let us say that I wish to retain the radial direction term, and because the cylinder is a regular cylinder, so I can say that this term is going to be equal to 0. There is theta symmetry per se in as far as the discussion is concerned. It is a regular cylinder. Similarly, I am not assuming any heat transfer along the z direction. So, as I have indicated, I am assuming that the cylinder is very, very long, and then we introduce the term which we call as an infinitely long cylinder. So, I am considering a steady state heat transfer phenomena in cylindrical polar coordinate system, okay, where the cylinder is infinitely long and there is theta symmetry. Properties remain constant as I have written earlier, and there is no heat generation term itself. So, therefore, if you look at this particular equation, then in that case the governing equation will look like that is the characteristic equation. And again, this will demand that at two values of R, I will require the values of temperature itself given. So, I can say that let R is equal to R0, T is equal to T0, and R is equal to RL, T is equal to TL. The infinitely long cylinder, mathematically, cylinders are never infinite, but in physically cylinders are never infinite, but mathematically we can treat cylinders as infinitely long cylinder when the L by D ratio of the cylinder is greater than or equal to 6. Otherwise, what happens basically, there is just like the way we were talking about the entrance length in a fluid flow problem. In this case, what happens? We have an end effects, the top end and the bottom end of the cylinder. If you are talking of a vertically long cylinder, we will have the temperature profiles deviating from what could be predicted on the basis of this differential equation alone. So, if we have a cylinder where the length of the cylinder is greater than 6 times its diameter, in that case the end effects can be neglected, and you can say, sir, everywhere the temperature is going to be more or less same as at the center of the cylinder, this will exactly match with this, but if you go towards the either ends, in that case there may be some deviation, but that deviation can be expected to be minimal once this criteria is satisfied. So, our definition of a mathematically infinite long cylinder is infinitely long cylinders are those whose lengths are greater than 6 times the diameter of the cylinder. Now, we can visualize various domain. Okay? We can have a cylinder, we can have composite cylinders. We could have said that, look, I have a cylindrical space. So, there is a cylinder sitting here, infinitely long cylinder. And I think of a enclosure which is also cylindrical in geometry, and this cylinder may be maintained at a constant temperature. So, I am not trying to find out the temperature profile within the cylinder, but rather I am going to find out the temperature profile in this particular space. Okay? Then closure. So, this is, it is maintained at a constant temperature, it is giving out heat, okay, because the surrounding is at a lower temperature, and there is a variation of temperature along the radial direction, and in terms of cylindrical coordinate system, that could be given here. So, I can say that if the axis is this, so this is the radial direction, this is okay, I would say r is equal to 0, then what I have given there as a boundary condition is r is equal to, so this is r 0 and we have t is equal to t 0 and we have said that r is equal to r L and t is equal to t L. One boundary conditions could have been that as r tends to infinity, okay, then what happens? The influence of the cylinder is not felt. So, when r tends to infinity, I could say that I could have written that r tending to r is equal to infinity, T is equal to T infinity, which is actually the room temperature per se. If the hot cylinder is sitting there and I am sitting, I am standing here, in that case I am experiencing whatever is the surrounding temperature, not feeling the influence of the cylinder at all. So, you can pose the problem or set the problem with any kinds of boundary conditions that you want to do. Now, let us look at the definition of the heat flux. So, we have QR is equal to minus K, the same Fourier's law applies here, okay, and we can say that QR into dr is equal to K over dt. We must understand that in this one dimensional problem, the QR is not constant. So, you can imagine it is the QR multiplied by the product area that remains that decides the net rate of heat flow. So, there is no, the heat flux closer to the axis is much higher intense than the heat flux which is far away from the cylinder. That means, as you approach the center of the cylinder, the flux increases. On the other hand, you move away from the center of the cylinder, the flux decreases, but the net rate of input of heat or flow of heat at this point which is equal to QR multiplied by 2 pi r. In this particular case, the area is QR into 2 pi r0 is exactly same as QR multiplied by 2 pi RL, because it is the net rate of heat flow under steady state condition input, rate of input. The statement is, if you remember, output, rate of output of heat is going to be equal to rate of input of heat, because the generation, I am not considering any generation itself, it is a steady state, no accumulation. So, that applies, and this is in watt, this is in watt, this is flux into area, this is flux into area. So, the flux into area evaluated at any point should come out to be equal to 1. So, we say that QR is a function of R. So, therefore, I cannot really integrate this from R0 to RL, which is T0 to TL, and this integration cannot be performed until and unless I know how QR varies as a function of R. So, the variation of QR as a function of R is to be substituted into this equation in order to integrate and obtain the resultant expression. So, now if we look at a cylindrical shell here, and as I said indicated that we have QR into 2 pi r, okay. This is the area which is at, suppose this is at r and this is at r plus delta r, a general case of shell balance again. So, this is evaluated at r and this is evaluated, okay, QR into 2 pi r, r plus delta r, and this is going to be equal to 0, because I have just now explained the product, or I am saying that q r into the area evaluated at any point r is exactly equal to q r into 2 pi r evaluated at a different r itself. And again the linearization and all, then you can see that this will give you an expression where you will find out that r times q r is equal to, that is what will be the net result from this. If you simplify, so this term is going to be equal to this term plus some derivative term, and that derivative term is going to come out to be, which essentially tells us the same thing, that r into q r is equal to constant. If that is so, let us say that this is equal to beta. So therefore, q r is equal to beta by. Now I have obtained q r as a function of r. I can go back to this equation. So this is going to be beta by r and then dr differential r. So I should be able to integrate this without any problem. It's a straightforward case now, and let us put the final results here. And the final result will look like integral, we have T0 to TL, and then we have beta divided by r, and this, and here we have k into delta t, and that delta t I have defined as T1 minus T2, because I have eliminated the negative sign here, and this therefore gives us that beta ln TL, sorry, this should be actually RL, and this should be not T1, T2. So this should be T0 minus TL as I have defined. Let us be consistent, and this is R0. So this should be RL by R0 is equal to K times delta T. So therefore, beta, which is constant, comes out to be K delta T ln RL by RC. Note that beta is a constant, my thermal conductivity is a constant, delta T are the boundary temperatures which are also given and constant, and RL and R0 are also constant. So therefore, this entire term is equal to constant, and now I should be able to find out that what is that thermal expression here. So if I substitute into this, the flux expression can be, so q r is going to be equal to k times delta t ln, and that r is going to be there, r ln R0, and this is the expression RL by. And therefore, you can see that the definition of thermal resistance now has increased, ln RL and R0, and then the K has come here. So this is divided by earlier. What was the thermal contact resistance? The thermal contact resistance was defined as delta X by K. That was the thermal resistance, in terms of flux. So I have defined it in terms of flux. So if I multiply it by area, in that case also I can do it. So there is no problem. Then the RR will cancel out. So I will multiply it with QR into 2 pi R. So that 2 pi R, this R will cancel. Only the units are going to change. So when I have said it is QR, so it is understood that I am talking of Kelvin per watt. That is the unit in which it is going to be expressed. And here, instead of delta x, this parameter r ln RL by R0 has come, and this ln R0, this parameter is in place of delta x, has come because of the different geometry altogether, but nonetheless this represents a length scale because this is dimensionless. So therefore, we see that the thermal contact resistance, so the thermal contact resistance in the cylindrical coordinate, I should be able to write that this is equal to R thermal in R theta z coordinate system as a function in R theta z coordinate system. This does not mean that, so I would say this is confusing. So, I say in cylindrical polar coordinate system, polar coordinate system. So, the thermal contact resistance is essentially R ln RL by R0 divided by capital K. So, you can remove, erase this, and that is the definition. And as you see that, so now if you have composite materials, composite cylindrical samples, so we should be able to find out that what are the span length, what is the corresponding radius, okay, and we should be able to calculate individual thermal resistances, take the delta T, and then we should be able to find out that what are the. So, suppose if you have now, I say that I have a hollow cylindrical passage through which the fluid is going, and then I have one layer of cylindrical insulating material and the other layer of cylindrical insulating material, then I should be able to find out that what are the thermal conductivity of this, because I know the thickness of this, I know the thickness of this. So, I can take the delta T between these two surfaces, and then I should be able to find out, if I assume the contact resistances for the time being, that what is the thermal resistance of this in terms of this, because this will be my R1, R2, this will be R2, R3, and then I should be able to find out that what is the contact thermal resistance with respect to flux, and then with respect to net rate of heat flow, then the R term will vanish. So, I should be able to find out the contact thermal resistance here, contact thermal resistance here, add them up, okay, and then delta T divided by the summation of the contact resistance will give me the net rate of heat flow, which is Q, provided I evaluate the thermal conductivity, thermal resistance, by multiplying with R, so that this R does not remain in the expression itself. We will solve some problems, and then you will have practice that how this typical parameter, this typical problem is is very important in the context of, say, flow. You want to something is flowing, hot fluid is flowing through a pipe, and then you have certain insulations. You have seen maybe split AC, for example, you have seen the outside pipes. Okay? So, those pipes through which the cold air actually comes from the outside machine into the house, they are really coated with first maybe a layer of adhesives, or some kind of a tape, and then some kind of a insulating material layer. So, this is the kind of a scenario that is being depicted here, and there you see that the insulation is quite effective in terms of reducing the heat transfer from the outside into the, because this is a colder fluid, okay, flowing through the pipe from the ambient to the atmosphere itself. So, it protects or retains the heat or coldness of the air flowing through the pipe itself. So, in this particular cases, if you know this temperature, these are to be given to us, these are boundary temperatures. If these boundary temperatures are given, the span of the coatings on this particular circular tube is also given to us. In that case, we should be very easily find out that what should be the net rate of heat flow by simply adding up the individual thermal resistances. And if you want to add the thermal contact resistance in such cases, you can do that, but again I repeat that the thermal contact resistance will have to be given to you, but summing up all the thermal contact resistances which are operating in series, we should be very easily able to find out that what is the rate at which heat is leaving through any cross section. So, we will continue this discussion, and then I have one more problem to discuss. So, I have I want to do the cylinder. Now, Cartesian coordinate is done, cylindrical coordinate one dimensional case is done, and we have many applications actually. I have just, because this basic informations will be necessary to solve various problems or when you encounter different kinds of scenarios. Okay? So, I have just given you, shown you the path, and now you have to move yourself and see that how can you manipulate with the terms and different kinds of handle different kinds of problems. So, with regard to the cylindrical Cartesian spherical coordinate system also, we will solve one problem. Okay? And there also we will consider only this particular, that is the radial direction. So, what we have just now considered is a radial heat transfer phenomena, radial heat conduction phenomena in cylindrical polar coordinate system. We are going to do a same phenomena, same study in which we say radial transport of heat, okay, or radial heat conduction in spherical coordinate system, and there we will show that this term will also be equal to 0, this term will also be equal to 0, this term because of the theta and the phi symmetry, and then we will be retained with one single term. This partial differential derivatives will be total derivative, and then we should be able to. So, only the integration part is different because of r and r square appearing. You are sometimes getting ln logarithmic terms, sometimes you are not getting logarithmic terms. So, this is bringing in some additional features, but conceptually there is no difference whether you want to solve a one dimensional equation, a heat conduction equation in Cartesian coordinate or cylindrical coordinate and polar coordinate. And I will also give you an expression for a two dimensional solution for a two dimensional Cartesian coordinate equation. So, we will stop here and then we will continue tomorrow in the next lecture.